Hey, we're going to take a look at solving one-step equations today, and the learning targets for today is that you'll be able to solve an equation for x that requires one step. Always write like two steps or multi-steps and things like that, and then one step. I just got carried away with the plural. All right, so I want to demonstrate a couple of examples, but I'm going to illustrate each of the examples using algebra tiles. And if we were in a classroom sharing a physical space together, I would take the algebra tiles out of the cabinet and would have them on the table that we could see them. So basically, they are exactly what you see here. Um, there are, in this case, four different shapes, and the longer rectangle ones I'm going to use to represent x. It's an unknown. I use a different color for positive and negative x's, and for the constant, the number part, just little squares. So the dark blue one is positives, and the red one for negatives. So we can illustrate, like if I had an equation that said 3x equals 15, I can illustrate that with algebra tiles. And when I illustrate them with algebra tiles, I'm going to keep track of my two sides of the equal sign with this teeter-totter, because I want the equation has to stay balanced, and I want to use that teeter-totter to help us remember. If you put an extra kid on one side of the teeter-totter, like on the right-hand side, you have to put another kid on the left-hand side to balance the teeter-totter. Otherwise, it like tilts one side, and that's not what we want to do for solving equations. I mean, it's super fun on a playground, but it doesn't work for solving equations. We got to keep it balanced. Whatever we do on one side, we got to do the same thing on the other side. So 3x equals 15. So I got three of the x tiles, and on the other side, I got 15 individual little single tiles. And so the 3x's balances the 15x's. So it's a one-step equation because I just need to do one operation to find out how much x equals. So x represents an unknown number. What I know is that if I have three of those x's, it's going to be the same as 15 of these individual tiles. If I broke both sides of this equation into three groups, then that'd give me just one x, and whatever those 15 broken into three equal groups is, that's what x is going to be equal to. So I think in this case, probably we can see that, make that go off the page. If I break it into three equal groups, each one of the x's is going to get matched up with five of these individual tiles. Right, so this is illustration. So I have my equation, 3x equals 15. In order to solve to find out what x equals, I'm just doing backwards operations. If instead of the mystery number x being multiplied by 3, what I need to do is break that into three separate groups. We break things into groups by dividing. So I'm going to divide by 3 to both sides of the equal sign, just like I did the same thing to both sides of the teeter-totter to keep things balanced out, right? So the 3's are going to cancel here, and then x equals, and 15 divided by 3 is 5. Right, so we've done some of this before, and actually this is going to be a lot simpler than the problems that we did last week. Yeah, second example, we got x divided by 2 equals 4. So I've already got my illustration set up. I got my teeter-totter. I took half of an x, I ripped it in half. Ugh! So there's half of an x, and that is equal to 4. Well, I don't want to know what half of x is. What I'm trying to find out is what x equals. And so if I think about this intuitively, if I have half an x and that's 4, I could just like double it, right? And that would give me a whole entire x. So if I had another one of these and I could stick those together to make a complete x, I would have to also double what is on the other side of the teeter-totter, so it's going to stay balanced. Okay, with the equation, what that is going to look like is I look at the equation, I say, hey, look, this is x being divided into two parts, and each part is 4, but I want to find a whole x. Well, if I take each of those parts, the 4, there are 2 of them, so if I take the 4 parts and double it, that'll tell me how many parts there are altogether. Said another way, this x is being divided by 2, and so if I were to do the opposite operation, I could multiply it by 2. That would restore it to the whole x. And anything I do on one side of the teeter-totter, I have to do the same thing on the other side. So the times 2 and divide by 2, those are opposites. They will cancel, so I have x equals. And on the other side, 4 times 2 is 8. Okay, there is no requirement that you illustrate with algebra tiles or teeter-totters or anything else. I'm trying to just provide some explanation and illustration in a concrete way that will have this make some more sense. Third example, negative 3x equals 12. And so I've illustrated the negative 3x's with yellow to be negative, and there are 3 of them. That's the same thing as 12. Yeah, this illustration is a little bit tricky because negative numbers illustrated is always a little bit of a reach for some people to say, oh, that doesn't really make sense. So the obvious part is that if 3 of these x's is the same as 12 of these blue squares, I could divide everything into 3 groups. And so then group, each x is going to get grouped with 4 of these blue things. Okay, but I don't want a negative x. I'm trying to find out what a positive x is. And so this part doesn't really make sense with the teeter-totter analogy. But if I do the opposite of both sides, instead of a negative x on the left and positive 4 on the right, if I do the opposite of both, it will still stay balanced. So I can switch the yellow to cyan or light blue, and then I could switch these 4 dark blue squares to red, um, representing negatives. And look, oh, whoops, that's the wrong part. Change the color. And then on this one, change to cyan. Okay, so then positive x equals negative 4. From the equation, how do I get there? So I get negative 3x equals 12. So the negative 3, I'll just keep that together as one thing. It is a negative 3. So to get the x by itself, what I'm going to say is, look, I had an x, I multiplied it by negative 3, and that gave me 12. So I need to work backwards. If I were to undo that multiplication by negative 3, that would put me at the original unknown number. So since the negative 3 is being multiplied onto the x, it tells me I need to do the opposite, which is divide. So I'll divide by negative 3. I can use parentheses to keep that negative sign attached just for clarity. The negative 3 times negative 3 divided by negative 3, those are opposites, and so they will cancel. So I'll have x equals. And on the other side, 12 divided by negative 3 is going to be negative 4.